CLion, a cross-platform IDE for C and C++. Download now.
Hello, everyone. Welcome to my presentation for today's topic. My name is Larry. I'm a software engineer with more than around 20 years experience from like C and C++, modern C++, software developing. So recently during the immersing of the AI, we have take advantage of this trend and developing some new library which is a fixed parsing like protocol library, which has been increasing. The performance has been increasing quite a bit compared with other existing fixed library. But we take advantage of the modern C++ to do this library. So let's dive into what's the techniques that we are using inside this library. By the way, this library is actually called NexusFix. It's an MIT license. It's currently in open source in GitHub. So it's using C++ 23, I think at the moment. Yeah, GCC 13. I can't remember what's the exact version of it. So it's supporting that version, and also it's a head-only core zero allocation hot path. Our target is to meet sub 200 like nanoseconds execution report parsing, which can be a alternative to QuickFIX, which is at the moment very popular, like in GitHub as well. That's the latency sensitive system. So for the protocol, if you are doing the trading, the financial, this is a protocol for financial information exchange. It has a special format which is tag and value pair separated by this SOH like separator thing. So it's so in a global like equity order flow, it's I think this one consume 70% plus. We can check this information online. So it's the format is looking like this. So it's about 30 fields per execution report. Strategy is read 5, 10, something like that. It's something like that. So still going back to the latency problem. So we have. So it can be up to 5. It's very usual. Sometimes it happens like 5,000 nanosecond, like nanoseconds. So runtime, it basically manipulates the string operation, manipulate the string, and also there's a for each field there's a runtime string operation. So it can be used the map and order the map, which is like the hash table in other language can be used for the field storage. There can be some dynamic memory allocation per message. Typically for the execution report pass, it's 2K to 5K nanoseconds. For P99 latency spike, it's 10 times or 50 times as a median value. Yeah. So remember though, if you have, bear in mind, if you have 100 nanoseconds in advance, that means that you would have a bit competitive edge towards the other one. So P99 spikes causing misfields. It will causing a bit problem if we have P99 spikes, and it can be a disaster in the trading. So the goal for us is to reach sub 200 nanoseconds. By the way, if you have any questions, you can put in the questions. I think there's a question and answer section, but maybe you can put it there. Yeah, this one is a metric. So we measure this this metric, and the target at the moment we achieved our target. This is the achieved ones, and we also did a comparison of the benchmark. Yeah, it's a quite a bit increasing. So for the parsing, for the FIX parsing, there's a two-stage parsing. We have a structural scan for the raw data, and also we have on-demand in a first stage, and in the second stage we have a on-demand access using. So in a stage one, we're using a SIMD scanner. Try to take advantage of the hardware capability for AVX2 or AVX 520 if it is 512, if it is 512, if it is support. And then we store it, and then we do a field like index lookup, like field request for the index looking up. But we are actually using there's in a later parsing we would have a PMR using direct access to memory without any dynamic memory allocation. So this can be found in this header file. And also the libraries has this approach is actually the concept has been referring to the SIMD JSON. So we have a JSON parser, so which is written by I think Daniel Lamar. So his library he's actually at the moment very fast JSON parser. So but he has a concept. I think the similar concept for that one, for the two-stage one. So, but we're using this concept to implement the to parsing the FIX protocol. This NexusFix library adapt this concept. So for that, for the technical one is a SIMD, which is a single instruction motive data. So we fetch, we just try to utilize the hardware performance, hardware like capability. If it is, we are not using the scalar. If we are trying to avoid the scalar thing, try to get a one by one, but we are trying to just use the hardware to fetch more data at once. This is one. You can see if we have using the same like approach. This is the AVX2 code. Yeah, we basically load a chunk of data, not a single byte, and then calculate the mask. So this is if the hardware is supporting AVX 512, then it would be like this. Yeah. So this is when the library start up. So it would try to detect at a very startup. It will try to detect what's the hardware's capability, and then we will try to select which method should be used. So there's no virtual function. There's no branches on the calls. It will directly using the method that we are using for the fetching. That in the library there's also a variable which you can choose to override when we are do testing. So this is actually the benchmark result. Compare using different buffer size. Yeah, we have compared with the Scala method like approach with AVX2, and also it's increasing. So by the way, the benchmark is actually based on one of our dev server. So which is the dev server is Intel Core i7 14700 KF, like this 5.7 gigahertz, 64 gigabyte memory with this kind of cache. So this is the hardware benchmark device that we run this test. Yeah, so this we can also inspect the assembly output from the compiler. So it's actually, yeah, this is the embed. I think this is the embedded assembly. So do we have a VP broadcast B, something like that? This is sets. This is some setup, and also these special instructions. So the other technique we are using is actually the PMR, which currently is supported in C++ 17, I guess. So that's the memory allocation stuff. So for malloc, which is it can be very expensive. It's a system call which hits the kernel, and it has unpredictable latency depending on what size or what you are allocating, and maybe it's also related to the system. When if the resource is not enough, it will give more. It will allocate more, and it will cause P99 spikes. So if any, yeah, OS management page default TLB misses. So this all would cause the P99 spikes in the trading. I think this is not allowed. If 99 spikes, so 99 will be causing this trading system came about worst case, not average. So P50 medium is okay. Medium fast. Medium is actually. So if P99 spikes, that will be problem. That the trading people would know. So I'm actually not a trading expert, but I think the trading guys. So they would have this numbers would affect them. They would try to avoid these spikes. So for PMR in C++ 17 standard, it's already in C++ 17 standards. So we actually so we can use like that. So we allocate a big buffer using std array, align 16, for example, 64 bytes, I guess. So align. Then we do a fields, and directly using this monotonic buffer resource, the pool, and then we do a reserve. We pre-allocate the buffer. So there's actually, by using this, there's so there's in the middle of the operation. There's no free trickling overhead. If you finish the whole thing, then at the very end, with the release will be release the entire buffer. But actually, this buffer is located on a stack, so there's no heap being involved. So for by using after using PMR, so we have a P99 test and before using and also after using. So so the mean is actually improved 1.5 times. For P50, it's roughly, it didn't change much. So it's in nanoseconds, it's slow a bit, but it's still, yeah, it's but the main thing is like P99 has been dramatically improved. It's nearly 14 times. So the latency range has been also increased quite a lot. So PMR increased the P99. By using PMR, the P99 has been improved. So yeah, then this we can say probably this PMR technology the technique we are using that would eliminates the tail problem of the P99, not the median. Yeah, this is more the concept that the trading people would know. That. So for without PMR, so this is the P90. So it has so it is a P50 27 nanoseconds, and P99 is 781. All these numbers are based on the testing, the benchmark on our development machine. So it has a spike, so it's unpredictable. So but with PMR, so we have very maybe in the initial time we have a very deterministic flat line here in the middle. Yeah, this is, they say, if you would lose money on P99 spike that arrived 10 milliseconds late. So deterministic faster. Actually, in this library, it's achieved both. For another technique that we are employing is the structural indexing. So in traditional parsing, it would scan the whole the entire message for each field lookup. So something like it's looking for a tag, and then looking for another tag. It costs it has a big O of n times k, where n is message size and k is the fields that needs to be assessed. So for the structural indexing, so index layout would be something like so we define this structure. So array size of it's you assign into the 16 SOH position equals, and then count size. So we are doing the field bounds within a constant expression through array 4. 4 of you assign integer 16. Yeah. So by using the structural index, the benchmark we have done is speeding up for single field access 4.5 times. For 5 field access, it's 3.6 times. for the full message parsing, it would be 4.4 times increasing. So with SMD, with synergy with SMD stage 1, SMD builds the index stage 2, use it. Combined synced scan and structure index. At the end, there's a sub 150 nanoseconds end to end. Yeah, another technique that we are employing is the SBE binary encoding. Yeah, so it's by having this fixed text protocol that we did a SBE simple binary encoding, so flyweight pattern. So it is similar type like this. We have a binary and also a fixed offset. Yeah, this is the SBE flyweight pattern code. Yeah. So it has a runtime. It's a compile time evaluation byte by byte. So if this by having this code, the compiler will try to we will try to make the code when it's in compile time to generate to calculate the value when you read that. If the compiler cannot cannot calculate the, in the end it would try to use fall through to the memory copy, which is in the runtime. Yeah, this is the benchmark for separately for the SBE when employing the SBE. So by decoding the decode P50 and decode P99, it has. So if we have pure fixed test, and also by using SBE binary, it has a speed up for 5.5 and 5.5 for P50 and 99 respectively. For the encode itself, it's improved by around 29 times. So by using the SBE, the memory, the reduction for each message, it has been reduced from like 200 byte to 60 byte, 64 byte, for example. It's yeah. Now, another technique that we are employing is the log-free deferring processing. So for this is to solve the problem which is non-critical work on hot path. So for example, if for the hot path, the flow would be like this. We have pass, we have it's a serialized thing. So we have a pass, we have a validate checksum, log persist, and root to strategy. Then when we do the default non-critical work via log-free multi-producer simple consumer queue, so we have pass, then we root to directory and send the other parts to the MPSC queue, twist queue, which is under background thread, which is similar, which is actually doing the checksum plus log and persistent, which is kind of they are separate. They are separate. They are two different independent paths. So it would save us quite a lot actually. It's saved us from 800 nanoseconds to 130 nanoseconds. Deferred processing. What moves hot off the hot part? So this is the one that we found for parsing message. It's critical for routing to strategy is critical. So it will be stay in the hot path. For the checksum and logging and persistence, it's not. So we will defer this processing in a different and put in a queue to process. So checksum validity before business logic acts on the message. So MPSC queue overhead is actually 30 nanoseconds per queue, per in queue. Yeah, by having deferral processing, the logging checksum percent totally being eliminated from the hot path. So it's 100%. The hot path still running, so it's reduced. Yeah. So maybe someone is sending some messages in the room, but I couldn't see at the moment. I'll check afterwards. So another technique we are employing is assume align to tell the compiler the pointer is actually guaranteed guaranteed aligned by a certain byte. So zero runtime cost, pure compiler hint, generates no instructions, tell the compiler what you know, which is yeah. By having assume aligned, the path latency reduced 17%. The instructions has been less, 6% less. So no code changes runtime. Compiler generate better instructions. Works with synced. Aligned loads are faster than unaligned. Smallest individual impact, but essentially free. Combined waterfall. So for baseline, for the QuickFIX baselines, for example, it's 5,000 nanoseconds. After synced technique used, it's already 380 nanoseconds. Then after PMR, it's 320 nanoseconds. After structure indexing, it's 210 nanoseconds. After simple binary encoding, 180 nanoseconds. After defer processing, with the lazy evaluation, it is 155 nanoseconds. After aligned, assume aligned, it's 143 nanoseconds. Total improvement, it's like quite a bit, 33 times faster. Yeah, these techniques are not purely multiplicative. Sometimes some overlap. The combination matters more than any single technique. That's so the end-to-end result. So we have compared with this, the improvement part for the execution report is 33 times improvement. Per message latency is less than 1 microseconds, 10 times faster. hotspot allocation modded? None. So there's no hotspot allocation anymore. So for the P99 and P50 ratio for QuickFIX is more than 10 times ratio, more than 10. And now it's less than 1.5, which you can be looking at I think this ratio is towards one. Towards one, the more you are towards one, the better. Yeah. So P99 stability comparison. So for existing QuickFIX, we have 5,000 not to 5,000 nanoseconds. It can be spiky and unpredictable, which has a range of around 8,000 nanoseconds. But in the library that we are developing is actually the NexusFix, which is actually time deterministic with a range of 25 nanoseconds. So with C++ 23, so we managed to we managed to implement a function that has 1,000 line into 10 lines. The same functionality that requires 1,000 line in the C++ 11 template method programming, but we managed to use it to implement it 10 lines using 23. It runs as compile time, not runtime. So what we did is we're using consteval, tag lookup table, and also concept, and also this if consteval dual function and this string consteval string hashing. So by looking at this consteval tag table, we can see if we are using the runtime switch and mapping. So we can use something like that. So switch case, and return a particular the different mapping thing. Then if we're using a compile time array using C++ 23 by using const eval with this pseudo array tag entry and this kind of thing, this will be generated in compile time, and the compiler will create a tag table for you. So we can directly using O1 when using no branches, no hash lookup, single array index. So we have been using concept to replace SVNA from 200 line to 25 lines. So by using SVNA in old C++ 11, we basically using enable if whatever thing, and this enable if can be a little bit tricky to read sometimes. But in C++ 23 concept, we can use something like this. We can define if this kind of has on app message, has on send message, the concept, and also session handler. Something like a concept that combines different existing concept that could give you a constraint, a type constraint. So yeah. So if we're using the const eval, so that means that we can combine two functions. The two functions will become one. For the old for the maybe C++ the before maybe 11 or something, we are using two separate functions for read LE runtime we have a read LE const expr. So this is so it's up to the caller to choose which functions that they should call. However, if we can use the C++ 23 with a consteval, we can just write one function with called readLE, and we can just try to let the compiler calculate because it's a const expression return value. So it would tell the compiler that you need to calculate for me as much as you can. Unless you cannot, unless the compiler cannot, then it would fall through the default runtime thing. So for the consteval string hashing, it's a switch on strings. In the old C++ or the latency C++, the runtime string comparison chain would be something like the equals operator, like using a string comparison with this one. This one is when you compare this, if the message type is a string, it would and this would there will be, I think there will be an implicit implicit type conversion from this type to a string type. Then it would handle it would call this handle as well. So it is kind of there's so many branches here, and each branch there will be a string comparison, and then new dispatch. So for C++ 23, it's a compile time hashing plus jump table. So we basically define a const eval, and this one define a user literal is a hash, and which will be generated a compile time value. This hash will be compile time hash, and then you can do a switch on this compile time hash with this case literal checking. So it's compile time constant, and it's dispatched to this handler. So for the compile time versus runtime summary, what runs. So this is the summary of each category that we are using that correspondent to the C++ 23 for tag metadata 200 match switch. That's const eval by array in binary. String hashing 30 is and the one on every message pre-computed const eval constant. So it's also type validation. Before it was sfine, and now we are using concept, error handling, try catch. Oh yeah, the expected I haven't checked yet. So but from the for the error handling, before it was try catch, which is unpredictable. Now we explicitly using stood expected, which is more deterministic. For the ending convention, ending convention, separated const expr and runtime. In the old C++ with separate const expr and runtime method, but now we are using const eval for single function with a single function price, and also we can define the literals for price quantity with new C++ 23. Yeah, so 500 values pre-computed, 0 runtime init. So we do, for example, we define the literals for price, quantity, and sequence with a return type of its respective return type, but it's a const eval. Yeah. So yeah, this is the short benchmark, the short video I recorded from the testing. There's a build and benchmark demo. It's is it running? Yeah, it is running. So we have this head-only parser and build using CMake toolchain and run for different benchmarks. Yeah. So we have same scanner benchmark test running. Yeah. We have the same like we have, I think we have the P. Yeah, this is the same the one, right? So this is benchmark for same. So let's see next one. Okay. Yeah, this is mainly to measure the P50 and P99. Yes. Let's see. Yeah, structural index bench. So this is the structure index bench. Yeah, just this is the assembly inspection. Yeah. All right. That's the small summary of from different C++ standard for the compile time evaluation. So we in olden time C++ 98 we use define as a macros, and then we have const expression, which is a compile time evaluation limited version, and also this sfn type constraints, and it's basically very hard to read. And static assert for the compile time validation. Now, gradually we have relaxed const expression, loops and branches in const expression in 17 const expression lambda function and compile time code, string view PMR, 20 concept, const eval, which means it is a guaranteed compile time execution, and span. There's quite a lot of spans being used in a code. I didn't see much coroutine there. Yeah, there's a coroutine, I think. For 23, you can use const eval, if const eval, dual compile runtime in one function. Understood, expected, assume aligned. Deducing this, did you CRTP replacement? Oh, yes. So each standard move more work from runtime to compile time. C++ 23 is a tipping point. Standard standing on shoulders. Well, some of the concept in the library we are employing is we refer to people's great ideas, like Daniel and Pablo. They have this themed and structure indexing and PMR proposal. And also, so I think that this project has been referenced. Yeah, log3q pattern and portable sim library from Google. The language didn't just get faster; it got smarter. What was runtime is now compile time. What was 100 times now 1,000 times now 10. What is now 1,000 lines now is 10 lines. So using the tools that the C++ committee gave us, yeah, that's pretty much it for my talk for today. It's just go through our project, and also this project can be found on GitHub under Silver Strings AI NexusFix. You can contact this to us if you have any questions. And it's yeah, we also to be honest, during the implementation of the code, we have been utilized the AI. We've been talked to the AI to try to refine our code. So some of the concept we are employing is actually we talk to the AI and do a pairing session with AI to refine our code. Because human beings, that's under the hood. That's the background that we did. But we always do the benchmark. We always run the benchmark. So that's really important. All right, that's I think that's pretty much for the talk for today. Yeah, thank you.